OK, so how do we find the resultant of tau? We use equilibrium, and we integrate the stresses over the surface. So let's find the resultant from this tau distribution on the surface. So let's draw it. Let's say that you have a shaft like that. And I'm just looking at the top now. And I want you to notice that I'm making my surface kind of thick because I want space to draw. But in your mind, always imagine it thin. OK, so this is my shaft. And there is going to be shear stresses on top of the shaft. We said that. Like that, all the way around. And so on. Now, what we're going to do is we're going to take a particular, let me cut here. Let's start from here. And let's take a little area of the shaft. Let's say that I take this area here of the shaft. And on this little area here of the shaft, the tau looks like that. You see? I'm taking this one, and I'm taking the one that's straight opposite to that, this one here. So they are on the opposite side with respect to the center of the shaft. You see that? I'm taking this guy and this guy here. So on each of these little areas here, I get a little force, which is equal to the shear stress times the area of this thing. So if the thickness of the wall is T, so let me write it as tau times the area. So if the thickness of the wall is T, the area is going to be the thickness times this length here. So I need an angle. So let's start making angle theta. So let's say that this is 0. And this angle here, let's call it d theta. OK, so I'm going around the circle. And I'm doing a little angle d theta as I walk around the circle. You see that? And I isolate this little chunk of the wall. You see? So my area here, where the tau acts, it has a width T, the thickness of the wall. Remember, T is whatever that is, stays. And the length here, if the radius is r, what is this length? Who is it?
R d theta.
R d theta, exactly right. So on this little chunk, I have a force dF. What about this other chunk? What do I have there? The same. Do they point the same way or opposite? This goes around that way. This comes back that way. This is going to town, come back from town. Right? They point in opposite direction. So this thing and this thing, what are they doing for me? What is that? Because they're equal and opposite. Is that a force? What is the resultant of these two forces? Does it give me a net force? No, because if I sum them, one is the opposite of the other one. This is a force couple. Blank, did you see the movie on Forces and Moments? See, very good. Your Italian is impeccable. OK, so the forces are dF. So together, I have a force couple. So I have dF on that side. I have minus dF on the other side. So together, I have a force couple. So they give me 0 net force. You remember before I wrap this thing around, I could sum all the tau over the area, and I got a shear force because they were all pointing the same way. Now, because for every side, I have the opposite side, and they point in opposite direction, these guys give me 0 net force. You see? But what do they give me instead? A torque. They give me a moment. They give me a torque this way. Right? Because if I look at the dF and I multiply by the arm of the torque, which is from here to here, which is 2 R's, I get a torque. So I get a d torque, which is equal to the dF multiplied by the arm of this force couple, right? The arm is 2F. The magnitude of the force is dF. The distance is 2r. I get this elementary torque.
This is what?
This is a moment. It's a torque.
Where did you get 2r from?
This is the arm, the distance between the forces in the force couple. This is the magnitude of the force couple. So,
where does 2r come from?
oh, if from the center is r, the distance between the two forces is 2r.
Is that tau?
Now, we have to be careful. There is going to be two guys that look kind of like the same, but there are important differences. This is tau, stress. A big one, and it has this thing in front of it. See this thing in front of it? It's a capital curly T. Capital curly T. Okay, you know what? We have an alphabet with only 26 letters. We steal some from the Greeks. We got some more. There are so many characters in this class that if I'm not creative, we do not know what to call these guys. So the rule is that internal resultants are always curly capital letters. Our resultant for the shear stress was a curly capital S. The resultant for the axial force is a curly capital N. And now, in torsion, the resultant is going to be a curly capital T. And this is going to be the torque resultant. Okay? The torque resultant. So these two guys give me a little bit of this torque resultant, give me their own contribution. So they give me a little torque resultant going out. It's the F dot dr, and if I put the F in it, which is tau t r d theta, and I multiply by 2r, this thing is the little bit of torque that this little area and this little area together give me on the shaft. So how do I find the entire torque? You integrate, right? So let me make a little bit of room here. So how do I find the whole torque? I integrate the whole thing. So the torque, to find the torque, I need to integrate around the shaft. So because I'm doing a couple at a time, I'm doing this couple, then I'm going to do the neighbors here, then this and this is going to go with this guy here, and I keep going around, 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 around. Do I integrate over the whole circle, or do I integrate from here to here? Half. Brilliant. Because I'm taking care of the other half in the force couple definition itself, right? So I integrate from 0 to pi, this whole mess over here. So I have 2r squared t tau d theta. That's it. Notice that there is an r in all these things. In all this integral, I am taking for granted that the tau is constant, that all the points are the same r. This is what I buy myself by doing this thin wall approximation. Okay? On Thursday, we can forget about this help from me. Okay? On Thursday, I'm going to hit you on the head with all the r varying from the center to the edge. But today, I'm totally nice. And so we only have one radius. So even I can do this integral, because the theta integrated to that gives me 2 pi, from these two, 2 pi r squared t tau. Okay? That is the sum of all the forces here over the whole section. And so together, they sum together over the whole thing, and I get one torque resultant, big capital T. This is my torque resultant. Instead of writing it this way, if you look at that, I can write it as, if I split this thing and I have, okay, let me multiply and divide by r. So I divide by r here, and I put another r in front. Now if I take 2 pi rt That is the cross-sectional area. You see that? So I can write this as the cross-sectional area times r squared times tau over r. And remember, this is the tau at radius r. So this thing is my axial force resultant. Okay, why do I split it this way? I split it this way because this thing, the area times the square of the radius where the area is with respect to the center of the shaft. If I take an area and I multiply by the square of the distance from the axis, do you remember what this is called? It's called the polar moment of inertia, IP, polar moment of inertia of the cross-section A. The area times the distance at which it is. If your area is at different distances, and we're going to do this on Thursday, so the general equation for the polar moment of inertia IP is the integral over the area of r squared dA. So that's the general one. So if you have, a whole solid guy, you need to integrate the areas multiplied by their respective radius to make the whole polar moment of inertia. But in this case, in which everything is at the same distance r, because our cross-section is a very thin rim, in which I have the whole area, all of it, at distance r from the axis, then my polar moment of inertia becomes very simple because r is constant, and I get A times r squared. Yes?
You said so tau over r is equal to
No. AR squared times tau over r times tau over r. This gives me so this is just the same thing. Tau is equal to this integral that gives me this expression. I can write this expression like this, and this gives me again tau.
So you have r 2 pi r squared t?
So I started off with 2 pi r squared t times tau. Then I multiply and divide by r, okay? So that I can group this guy here together, and that's the area, and end up with area times r squared times tau over r. I like to write it this way. Why do I like to write it this way? Because down here now, I can go back to what I wanted, and I get an expression for the axial torque resultant, which is equal to IP times tau r, actually let me make the tau r, tau at radius r over r. This is, let me make it a little bigger here. This is the equation that connects my shear stress tau to my resulting torque T. Is simply tau multiplied by a geometry thing, which is the polar moment of inertia. But how much tau matters is controlled by how far it is from the center. Because you can imagine that if I'm very far from the center or very close to the center, it's going to make a difference on how much torque the stress is giving me, right? So this expression here is the equivalent of this expression here. Here, my axial force resultant was simply stress multiplied by the area. For torsion, it's not as simple as that. Because what matters is not just how much area you have, but how far is this area from the axis. Because we're dealing with torsion. So it's a moment. It's not just how much force you have, but how much force times how much distance you have, right? So life cannot be as simple as that. I need a polar moment of inertia. And then this one is the one for the whole section. When I sum up the stresses, I need an R in there, because not all stresses count the same. Okay? So this one is the equivalent of my N, is the equivalent of this expression over there for torsion. That relates my shear stresses to my geometry, through my geometry to my axial torque resultant. This is a moment around the x-axis. The axial torque resultant is a moment around the x-axis, around the axis of the shaft. I did not even introduce an axis x yet. So if I have a shaft like this, a positive torque resultant, actually let me draw it the other way around, the way we do for axial loading. Okay, so if I have like that, a positive torque resultant comes out. So the positive torque resultant is something that looks like this on this side, and this one on the opposite side. This is a positive torque resultant. And another way of drawing the same thing is by drawing it with the axis of the torque, like that, and like that. So when I draw the torque, I can either draw the way it twists, like the fingers part, or I can draw just the axis. Remember, the axis has a double arrow. This is a moment. Okay? And the positive torque is something that makes me have a positive twist. Everything is consistent. The same way as for axial loading, a positive N comes out of the surface. So in axial loading, we had a positive N was coming out of the surface, and the negative N would squeeze the surface. The same thing for torsion. A positive torque resultant twists in a positive way, in a way the thumb comes out of the surface. So this is a positive torque. I don't care which way the x-axis goes. The same way in that case. Here, I didn't care which way the axis goes, right? If it pulls, its tension is positive. The same way this way. If it twists, like the black licorice thing that you got, it's a positive torque. Okay? When you draw the unknown axial torque resultant, you draw it with the double arrow coming out of the surface, the same way you were doing with N. Okay? All right, we need the last step. This one. Let's do this last step. So we have that one, we have this one. Essentially, the last step is I'm going to put together this, this, and that. Okay? Let's use it. So we have that the torque is equal to the IP times tau divided by R. And then we have the tau. So we have IP divided by R times our expression for tau. Tau is gamma times G. So this is IP over R times G times gamma. My gamma is phi over L times R. So I have phi over L times R. This guy and this guy cancels out. And so what do I get? I get equal to IP over L times G times phi. This is equal to my axial torque resultant. Just sub in and do the work. Look at this equation and this equation. My force resultant become a torque resultant. my structural deformation delta becomes my angle of twist phi. My geometry that used to be A over L is now IP over L. And my material properties that used to be E are now G. Other than that, small differences, everything stayed the same. Yes?
How do you go from the second step to the third step?
Just substitute. Substitute these equations in, and you find those. Okay? Pretty cool. We are done with torsion. Now we know somebody comes to us and gives us the shear modulus, and he gives us the angle of twist, I can tell you what torque there was. And if somebody comes to you and tells you what torque there is, then you can tell me the angle of twist, as long as you know geometry and properties. So now we go back to, OK, but what creates this torque? I say, if I come to you and tell you the torque, then you give me the angle of twist. But now, how do I find this torque resultant? We go back to how did we find the axial force resultant? We find the axial torque resultant the same way as we find the axial force resultant based on the loading on the structure, by putting the structure in equilibrium. Okay, so this is the last thing we need to do today. And because you're so good in axial loading, this is going to be fairly quick and painless. Okay, so one last step.